All right, so we are starting lesson 8 today, and lesson 8 is about trees. Basically, what this is another linked data structure where we use nodes and pointers. So far, the only thing we've used nodes and pointers for are linear linked lists, right? So this is a non-linear linked data structure. What you see here is an example of a binary tree, because each node in this tree has up to two what we call children, right? Up to two other nodes that it's pointing at. So there are a lot of different kinds of trees. You can have trees that have as many children where each node has as many children as you want. You can have trees where there are certain rules about how the data, where the different pieces of data go. So we're going to be talking a lot about that. To start with, though, there's just a lot of tree terminology that we're going to have to kind of get squared away with before we start. Anybody want to ask a question at this point? Okay. So let's see. Here we have, this is a tree sort of in the sense of like a family tree, right? I don't know if you've ever thought about this with family trees, but it's actually sort of an upside down tree, right? The roots at the top and the leaves are at the bottom, sort of. So that's what we have going on here. So this special node at the top is called the root. Each node can have a left child and a right child. In a binary tree, right? In a general tree where you can have more than two children, then you can't refer to them as left and right, obviously. So if you have a node that has no children, that's called a leaf. Kind of makes sense, fits with the analogy, right? So a lot of the rest of this is going to be pretty intuitive. It comes from the way we talk about a family tree. So the root, we could say the root is an ancestor of this node 13 down here, or this node 13 is a descendant of the root. We can say, we talk about parents, right? So the parent of 35 is 17. Okay, I think most of this is pretty straightforward, so just let me know if something isn't like crystal clear. Siblings, right? So 9 and 35 are siblings. This thing right here is one example of what we call a subtree. Okay, so there's lots of subtrees in here, right? Each leaf by itself is a subtree, so that's 3. And then I've got this subtree, that's 4. This right here would be a subtree, and then the whole left side would be a subtree, the whole right side would be a subtree, so lots of different subtrees here. We can talk about left subtrees and right subtrees. We talk about the depth of a node The depth of a node is the number of steps it takes to get from that node to the root. Okay, so the depth of this node 35 right here is 2, right? The depth of the root is 0. Okay? You guys are so talkative. So then we can also talk about the depth of a tree. And the depth of a tree is just equal to the depth, the largest depth of any node, or the depth of the node that has the largest depth. Not quite sure how to say that, but the maximum depth of any of its leaves. Okay. Full binary tree means that every leaf has the same depth, and every non-leaf has 2 children. Okay, so that's a very formal, sort of, maybe even hard to understand way of describing a picture that should be pretty easy to picture, right? If I were to draw a picture, it would look something like, I guess I can't, like, in Paint, can you open a new, I think you can't open a new tab, right, or a new,
you have to save this one.
I'd have to save this and then open a new one, yeah. I'm going to, anybody want to see me draw a picture of a full binary tree, or do you pretty much get it? It just means that there's no empty spots in it, right? So actually, I suppose if I were to add, let me ask this: how many nodes would I have to add to this tree to make it a full binary tree?
8. 8.
Yeah, I see. Yeah. Okay, so I have 4 and 8 and 6 so far. What are we coming to consensus? 6? 6. Sorry?
The 30 says 66.
Oh. Right. So let me just. So there'd be one here. Whoa. There'd be one here. Whoa. Why is he doing that? Too small, I guess. There'd be one here. There'd be one here. And one here. And there'd be one here. And one here. And one here, right? So 6. That makes sense. The idea of a full, I won't go there yet. Okay, so then there's something called a complete binary tree, which is not quite as perfect as a full binary tree. I think that's the easiest way of thinking of it. A complete binary tree is what you get if you always add nodes from left to right. So, and you always fill up one level at a time. That makes sense? So if you take a full binary tree and you add a node all the way on the left, it's no longer a full binary tree, but it's still a complete binary tree. That makes sense? So if I add a node down here all the way on the left, okay, now I've started a 1, 2, 3, 4. I've started a 5th level of nodes, so it's no longer a full binary tree, but it's still a complete binary tree. Okay? Yeah.
So if you put it on the 13, it would be neither full nor complete.
Correct. Yeah, if I put a node down below the 13 at this point, then it would not be a full, it would be neither a full binary tree nor a complete binary tree. So another way of describing the relationship is that all full binary trees are also complete binary trees, but not the other way around. Make sense? Okay. Where would the next node go for? Oh, after this. So, in order to keep it complete, I have to add the nodes from left to right, basically. So the next node would have to go here. Right? So I stopped drawing my lines. Maybe it would make more sense if I connected these all up. Right? Yeah. So what I have here is still a complete binary tree. Okay. And then the one other idea is the idea of a general tree. I think I mentioned that briefly already. And so there we just want to make sure you understand that what we're talking about here is a very special case of tree that's probably the most commonly used type of tree. But it's not necessarily the case that tree data structures always have to have be binary, right? In other words, can only have 2 children for each node. Okay, so let me find my notes. Okay, so the next the next term that I want to define is sort of turning a corner here onto a new topic, and that is I think I'm going to get rid of this whole picture here. Hold on. Yeah, let's do that. That's it. So we're going to take a long, close look now at things called binary search trees. Okay, and a binary search tree is just a binary tree where if you look at any node in the tree, all of the nodes in that node's left subtree are less than that node, and all of the nodes in that node's right subtree are greater than that node. Okay? So let's make an example. I guess I'll start by just drawing a bunch of nodes. And lines. Okay, and let's say we've got a 45 here, and let's say that I'm going to tell you that there's also the number 9 also occurs in this tree. Can you tell me what can you tell me about where it's going to go? One of these nodes over here on the left side, right? So I'll just, for kicks, I'll put it here. Okay. If I put it there, everything over here has to be less than 9. Everything over here has to be greater than 9. And what else? Less than 45, right? And then everything over here on the right has to be greater than 45. So 3, 17, whoops, 17, 20, 53. Okay, so one technicality, we have to figure out what to do with nodes that are equal, right? So we're going to say that everything in the left subtree has to be less than or equal to the node itself. Okay? Any ideas what the advantage of something like this might be?
Searching is really fast.
Searching is really fast. Yeah. So if I want to find the number 20, I don't have to start at the beginning of the list and look down the entire list until I find it, right? I can start here at the top, and I know that the number I'm looking for is less than 45, so I can completely ignore the right subtree and just look in the left subtree. And then I see that the node here is 9. That tells me that the node I'm looking for has to be to the right of that node, because I'm looking for the 20, and that's bigger than 9. So looking at this binary tree, I want to just talk for a minute about how efficient this might be. Looking at this binary search tree, what is the highest number of nodes that I might have to look at in order to find something I'm looking for?
3 steps. 4 nodes.
Yeah, I might have to look at 4 nodes, right? Okay. If I had, so let's see, how many items are in this one? There's 8 items, right? If I have a binary search tree that's well balanced like this, and it had, say, 15 items in it, what would be the most nodes that I would have to look at to find something? I made that way longer than I needed to. What's that?
Would this be equal to your tree, like maximum tree depth?
Yes, exactly. Well, one more than my tree depth, right?
Yeah.
Because
you count
each node, because I'm asking how many nodes you have to look at, not how many steps there are. So let's make a little table here. Number of nodes. So what I'm looking for here is I want you to tell me what is the maximum number of nodes that I will have to look at if there are n nodes in the tree, and assuming that it's balanced. I mean, there's, you know what I mean by balanced? Not perfectly balanced. There's no more than one. You fill up every level before you start filling up the next level. Does that make sense? So, number of nodes, max number of nodes that I have to look at. I'm not going to type that out. I'll have to remember it. Visited, I guess, is what I want to say here. Max number of nodes visited. Okay, in order to find something. So what we just said is that actually, let's start smaller. If there's one node in the tree, what's the max number of nodes visited? One. If there are 3 nodes in the tree, what's the max number of nodes you'll have to visit? 2. If there are 7 nodes in the tree, the maximum number of nodes you'll have to visit is 3. You're getting the pattern here, I guess. So the one that I had just asked you about was 15, and you said 4, right? What should we try next? Sorry?
23?
No. So,
31.
yeah, 31.
So it's 2 to the n minus 1 again?
Yes.
Same time as
Yep. Yeah, except, well, yeah, we'll go with that for now. So, if the number of nodes is n, the maximum number of nodes that we'll have to visit is, oh,
Plus 1?
no. So let me put this a different way, okay? If, so this is going to stretch your mathematical skills.
Plus 1?
You. But hold on. No more guessing. Let me ask it the other way. If the maximum number of nodes visited is n, then the number of nodes was 2 to the n. No, 2 to the n minus 1. Right? Let's just approximate here for a minute, okay? Can we just say, to keep things simple, let's just say 2 to the n? Okay? But that's not what I want to know. I want to know if the number of nodes is n, what's the maximum number of nodes visited? What's that called? Logarithm. Base 2. Log base 2 of n. How many people freak out when I say the word logarithm? Come on, be honest. I mean, I know when I was in your academic situation, I would have said yes. But this is actually a pretty pretty significant result that just comes up over and over and over again in computer science. Log base 2 of n. I'm not quite sure how I'm doing. That's pretty good. Okay, so remember last time we were talking about towers of Hanoi, and that was an algorithm that was really, really, really inefficient, and it was exponential, 2 to the n, right? Okay, this is sort of flipping that around. This is an algorithm that is very, very efficient because I'm doing the opposite of an exponent. I'm doing a logarithm, right? That's all logarithm is. It's just the opposite of exponent, right? Inverse, I guess, is the technical term. Inverse of exponent. Okay, so just to get you a little more comfortable with the log thing, maybe if I said n is 31. What's the max number of nodes visited? In your mind, what you're doing is you're saying, okay, 32, 2 to the what is 32, right? And that's exactly what what a logarithm is. 2 to the what is 32. In other words, what's log of 32? Let me say that one more way. Asking 2 to the what is 32 is the same thing as asking log base 2 of 32 is what? Okay. So I have to say for myself that when I studied math, I never really got logs. Then when I studied computer science, you pretty much have to get it. You know, eventually you'll get it. All right. Any questions about any of that? Okay. And we're going to be seeing a lot more of this log stuff in the next 2 weeks. So.
When you're adding nodes, how easy is it to keep the tree balanced?
Okay, excellent question. When you're adding nodes, how easy is it to keep the tree balanced? Not easy. So what we're going to do at this point anyway is we're going to just not worry about that and hope that it turns out to be somewhat balanced. And you know, chances are it's going to. But then, you know, in the next chapter, and I'm not sure how much detail we'll be able to look at this in, there's more advanced techniques of building these things, and that in order to keep them more balanced. But it's pretty hard, and it's typically something that you would study in like an upper division data structures class or something like that. Okay, so I guess we should actually try to write a little code here. Did you notice that we haven't even talked about computers or programs or anything like that yet? So let's come over here. And what I did here is I created this client program, which is basically exactly the same client program that we started with when we were doing our linked lists. Okay, so really what's going on here is this is just another way of implementing the same thing we implemented with linked lists, right? So from the client program perspective, there shouldn't be any difference, right? The only difference in this case is that I actually decided to call the class binary tree, so I have to change the type to binary tree instead of, I think before I called it int list type or something. But you know, that's not necessarily the case. I could have used exactly, if I had named my class correctly, I could have used exactly the same client program that I used before, right? So we're going to start by seeing if we can just do a print and an insert into a binary tree, binary search tree. Okay, so sorry, my notes here are scattered. So I'm going to start with, we need a constructor. So binary tree. And then we have our insert. And you know, just to keep things simple for now, it's going to be a list of integers. And then we need a print. Okay. As you know, probably if in a real live class we would not have a print function. We'd have iterators and all that, right? So, but just to keep things simple, we're going to do print. Especially since print happens to be like the easiest function to write. So private, we have, just like with the list, we have struct node. Okay, what's the difference in the node going to be now?
Data, and then we have the left child and right child.
So before we had data and next, right? Now we're going to have data and left and right. Okay, and then so our one actual data member, before we might have called it like head pointer or something like that. I'm going to call it root pointer. Okay, so then, whoa. What do you suppose we need to do in our constructor? How do we represent an empty tree? Yeah, root pointer is going to be null. All right, let's work on print because print's easier. All right, void binary tree : print. Let's write this function so that it prints the data, the nodes out in order, sorted. Okay. Any thoughts about how I might do this?
In order sorted?
Sorted, sorry, in order sorted. No, in order, it's sorted. Print them out sorted. In ascending order.
Okay.
So not representing the actual hierarchy of the tree.
Correct.
Okay, so flat structure.
I'm just, yeah, no, I'm not trying to represent the hierarchy of the tree at all.
Based on the data.
Yeah, I'm just printing the data. I'm just printing out the list, right? Just like if I had represented this with a linked list, I would just print out each piece of data one at a time. Yeah.
I guess just go through all the lefts until the next equals null.
Go through all the lefts until next equals null. Okay.
And you want to keep track of how many steps you took getting there.
Keep track of how many steps you took getting there.
And then once you print that one, you want to go back that many steps minus 1 and print the right. And then take a step back and go to the right.
Okay, so yeah, something like that. Complicated, right?
Yes.
Recursively, could you set the base case of trying to print the null node? That's your base case.
Okay.
And then print all lefts first, and then print all the right.
What do you think? That sounds good?
Sounds good.
So yeah. So the suggestion was maybe try recursion. We have base cases printing the null tree, the empty tree, and then the recursive case would be print the left tree and then print the right tree. Okay. Well, let's give it a shot. If I agree, that sounds like a better idea. If root pointer not equal to null, right? Sorry, I just want to check something in my notes real quick. Yeah. Okay, so, yeah.
If left is null, you print the data. Otherwise, you print left and print right. Does that work?
If left is null, you print the data. That's it.
I think. And print right.
And print right.
Yeah.
Otherwise, so if left is null, print the data itself and then print right. Otherwise,
Print left, print right.
print left and then print right.
I think.
Just one missing piece there. Print left and then print the data itself, and then print write. Okay, that would, I think that where you're going would work. However, what you're doing there is you're putting another base case in there that you don't need. So I don't have to check to see if left is null, because if I call print with, if I ask this function to print the left subtree and the left subtree is null, it doesn't do anything anyway, right? So I just need to say root pointer we're just about out of time. So we're going to finish this up next time. But you're on the right track.